History is often written as a sequence of battles, treaties, and political revolutions, but the true legacy of global conflict is frequently written in the ledger of peacetime economic growth. While classical economic theory often treats military expenditure as a sunk cost or a necessary burden for national security, the historical record reveals a far more complex and causal relationship. In periods of existential threat, the state assumes the role of the ultimate first customer, unburdened by the traditional market constraints of immediate profitability, cost efficiency, or consumer acceptance. Governments are uniquely positioned to underwrite the exorbitant research and development costs of radical new technologies. When geopolitical survival is at stake, military departments gladly pay massive premiums for incremental improvements in reliability, precision, and speed. This mechanism allows highly experimental technologies to cross the so-called valley of death in product development. By funding the initial prohibitively expensive stages of innovation and enforcing stringent quality control standards, military procurement de-risks entire new industries. Once these technologies are perfected on the battlefield, their underlying supply chains, manufacturing processes, and highly trained human capital inevitably spill over into the civilian sector. This spillover creates an ecological regime of innovation, birthing new commercial industries that dictate global trade patterns. From the copper-bottomed ships of the British Empire to the aerospace and semiconductor boom in Cold War America and the high-tech export economies of modern Israel and South Korea, the mass production of military hardware has historically served as the foundational catalyst for the subsequent economic rise of the nations that developed them. The unprecedented global dominance of the British Empire during the 18th and 19th centuries was predicated almost entirely on its ability to project naval power and secure global shipping lanes. A critical yet frequently overlooked technological leap that enabled this maritime hegemony was the adoption of copper sheathing on the hulls of Royal Navy warships. Throughout the Age of Sail, wooden ship hulls were highly susceptible to the teredo navalis, a voracious shipworm that bored into timber, as well as severe biofouling from barnacles and crustaceans. This biological accumulation drastically reduced a ship's speed, maneuverability, and lifespan, requiring vessels to be routinely hauled out of the water for laborious cleaning. In the early 1760s, the Royal Navy began experimenting with copper cladding its warships to prevent these marine pests from destroying the hulls. The early experimentation, notably the trials on the frigate HMS Alarm in 1761, revealed a severe engineering hurdle. Seawater acted as an electrolyte, creating a catastrophic galvanic reaction between the traditional iron bolts holding the ship's timbers together and the new copper plates. This reaction caused widespread corrosion, literally dissolving the iron bolts and threatening the structural integrity of the vessels. The resolution of this issue required a massive metallurgical pivot. By 1783, the galvanic-induced corrosion problems led the British Admiralty to procure a suitable, though highly expensive, alloy for hull bolts, utilizing either copper zinc or copper tin. Despite copper sheathing being roughly 6 times more expensive than traditional wood maintenance, Britain's supremacy at sea was deemed paramount. In 1786, the Admiralty ordered the re-bolting of every naval warship, bringing an end to the controversy and solidifying a new standard for naval architecture. The strategic advantages were immediate and profound. Below the waterline, the copper sheathing chemically reacted with oxygenated salt solutions to produce an oxychloride film and a complex of copper salts that dissolved gradually, making it nearly impossible for marine life to attach to the hull. Strategically, this allowed British ships to remain at sea for vastly extended periods. British Navy Comptroller Charles Middleton accurately estimated that copper sheathing effectively doubled the number of active ships at sea at any given time, prompting him to give coppering precedence over all other shipyard tasks. The economic spillover of this military procurement was staggering, triggering a massive copper boom immediately prior and during the dawn of the British Industrial Revolution. To supply the thousands of copper nails and the overlapping fish-scale sheets required for the entire fleet, such as the 12,000 feet of sheet copper required for the USS Constitution later on, the demand for copper skyrocketed. This massive demand created an ecological regime where the extraction of a single commodity drove a constellation of macroeconomic shifts. Extracting copper from deep mines in Cornwall and Wales required the constant pumping of water, a necessity that directly drove the adoption, refinement, and mass production of early stationary steam engines. Furthermore, the logistics required to manage this transition revolutionized the Royal Navy's supply chains, establishing a dockyard bureaucracy and lean efficiency programs that became the blueprint for modern industrial management. Ultimately, this military technology diffused into the English merchant fleet, securing the shipping lanes vital to the West African and Caribbean trade networks, and underwriting the immense capital accumulation that fueled the broader Industrial Revolution. Parallel to the innovations in naval architecture was a revolution in naval artillery and industrial metallurgy, spearheaded by the Carron Company. Founded in 1759 as an ironworks on the banks of the River Carron near Falkirk, Scotland, the company was established by John Roebuck, Samuel Garbett, and William Cadell. The company pioneered the use of Abraham Darby's method of smelting iron with coke derived from local coal mines, rather than relying on traditional charcoal. This advancement allowed them to push older charcoal-burning ironworks out of business, though their early operations were plagued with unskilled labor, financial precariousness, and harsh labor conditions that occasionally required military troops to quell disputes.
The company's fortunes were permanently altered by the influx of military contracts and the arrival of a new business partner, Charles Gascoigne, in the late 1760s. Initially, the carelessness of the workmen led to a deterioration in gun quality, prompting the Royal Navy to cancel its contracts in 1773 and order all Carron cannons removed from its vessels. Recognizing the need to regain the military's trust, Gascoigne developed a new type of naval artillery in the 1770s, famously known as the carronade. The carronade was a short, smooth-bore cast-iron cannon designed with unprecedented dimensional precision. Because the shot fit more closely within the barrel, more of the propellant charge's energy was transmitted to the projectile, creating a devastatingly effective weapon that used significantly less gunpowder. The carronade weighed a fraction of a standard long gun, required a much smaller gun crew, and produced a far gentler recoil. Initially developed to allow civilian merchant ships to defend themselves against heavily armed privateers without requiring reinforced ship timbers or large crews, the carronade fundamentally altered global maritime trade. British merchant fleets could now sail the globe heavily defended at a fraction of the traditional cost and weight. The weapon was soon adopted by the Royal Navy, placed on the upper decks of warships like Lord Nelson's HMS Victory to provide devastating close-range firepower during the Napoleonic Wars. The Duke of Wellington found them so effective that by 1812 he requested that only Carron-manufactured cannons be used in his army. The economic impact of the carronade's mass production transformed the Carron Company into the largest ironworks in Europe by 1814, employing over 2,000 workers. The metallurgical expertise developed through casting high-precision military ordnance created a hub for technological innovation. Renowned metallurgists like Henry Cort experimented with malleable iron at the Carron Works, anticipating the puddling process, while the company also cast the high-tolerance cylinders necessary for James Watt's first operational steam engines. Furthermore, the company expanded its global reach, with Gascoigne eventually immigrating to Russia in 1786 at the behest of Catherine the Great to improve her weapons foundry at Petrovazotsk. Following the eventual decline of naval cannon demand, the unparalleled casting infrastructure built by military procurement seamlessly transitioned into civilian manufacturing. The Carron Company utilized its military-grade furnaces to produce iconic elements of British infrastructure, such as the red telephone boxes designed by Sir Giles Gilbert Scott, pillar post boxes, cast-iron bathtubs, and the massive structural rings lining the Tyne and Clyde tunnels. The military demand for the carronade thus directly capitalized the heavy iron infrastructure that built the modern British state. The mid-20th century witnessed the United States leverage the existential crises of World War II and the ensuing Cold War to permanently alter the global economy, beginning with the absolute necessity of advanced materials. At the outbreak of World War II, the United States was deeply dependent on natural rubber, consuming 591,000 long tons in 1939 alone, heavily imported from the Far East. Following the Japanese expansion across the Pacific, these supply chains were entirely severed, plunging the United States into a severe rubber famine. The lack of rubber for tires, tank tracks, and aviation components aggravated downward pressures on total factor productivity across the entire U.S. manufacturing sector. Recognizing that this shortage threatened the entire war effort, the federal government initiated an unprecedented industrial policy. The government quickly consolidated the market, warehousing natural rubber across 135 heavily controlled facilities, and organized a massive consortium of industry and academia to synthesize alternative materials. Prior to the war, synthetic rubber production was virtually non-existent. In 1941, the U.S. produced a mere 231 tons. Under the mandate of wartime necessity, the state invested heavily in the construction of 15 standardized production plants. Ultimately, the nation spent as much on its synthetic rubber program as it did on the Manhattan Project that developed the atomic bomb. The National Institute of Standards and Technology, or NIST, played a vital role, utilizing thermodynamics to suggest synthetic formulations and standardizing chemical testing procedures using advanced instruments like viscometers. By 1945, the government-backed program was producing an astonishing 70,000 tons of synthetic rubber a month. The program produced approximately 1.34 million long tons of government rubber styrene, or GRS, during the conflict. Following the war, this massive state-controlled monopoly was gradually privatized and sold to commercial entities in 1955. The infrastructure and chemical engineering prowess funded by the government permanently altered global supply chains. By mitigating the volatile price swings of pre-war natural rubber, synthetic rubber became the backbone of the global post-war economy. Today, synthetic polymers, descendants of the wartime GRS program, account for 70% of all rubber used in manufacturing worldwide. This government-mandated military program birthed an international enterprise that generates over $60 billion annually and remains essential to the modern transportation, aerospace, energy, and electronics industries. Simultaneous to the materials revolution was the birth of the modern aerospace industry. During World War II, the United States Army Air Forces required a strategic superbomber capable of delivering massive payloads over intercontinental distances at high altitudes. The result was the Boeing B-29 Superfortress, a four-engine heavy bomber that required a national revolution in aerodynamics, manufacturing, electronics, and materials. The B-29 program was the most expensive military project of the war, costing $3 billion, the equivalent of $54 billion today, far exceeding the $1.9 billion cost of the atomic bomb. To build an aircraft capable of high-altitude flight, state-of-the-art technologies had to be invented from the ground up. The B-29 featured the first-ever pressurized cabin for an Allied production bomber, developed by Garrett Air Research. Engineers devised a complex system featuring a long pressurized tunnel joining the front and rear crew compartments over an unpressurized bomb bay. Additionally, the aircraft introduced dual-wheeled tricycle landing gear and an advanced analog computer-controlled fire control system that allowed a single gunner to direct remote machine gun turrets. Because the demand for the B-29 was so immense, with 3,970 ultimately built and a peak production rate of 375 aircraft per month in 1945, the government was forced to decentralize production. Boeing's plants were slammed building the older B-17 Flying Fortress, so new massive assembly facilities were built in Kansas, Washington, Georgia, and Nebraska, run by Boeing, Bell Aircraft, North American Aviation, and the Glenn L. Martin Company. This trained a vast new national workforce and permanently upgraded America's industrial baseline. The technology was so advanced that the Soviet Union immediately re-engineered captured models to create the Tupolev Tu-4, a carbon copy debuted at the Tushino Air Show in 1947.
The transition from military dominance to commercial hegemony was direct and swift. The technology engineered for the B-29 allowed companies to envision larger civilian planes capable of flying higher and farther than ever before. The B-29 airframe was evolved into the C-97 Stratofreighter for military cargo, featuring a unique double-bubble inverted figure-8 fuselage. By 1947, Boeing had adapted this design into the Model 377 Stratocruiser, the world's premier post-war commercial airliner. Utilizing the pressurized cabin technology and powerful engine configurations pioneered by the B-29, the Stratocruiser offered transoceanic range and unprecedented passenger luxury. Pan American World Airways and British Overseas Airways Corporation deployed these aircraft to conquer global flight routes, translating a wartime bombing platform directly into an American monopoly over global commercial aviation. The airframe proved so durable that it was later modified into the Aerospace line's Pregnant Guppy to transport massive components for NASA's space program. As the propeller era reached its zenith, the Cold War arms race necessitated the development of jet propulsion, leading to a massive spillover that created the modern commercial airline industry. The extreme costs of research and development required to invent the turbofan engine could not be borne by private civilian companies. Instead, it was underwritten by the U.S. military's demand for high-performance strategic bombers and aerial refueling tankers. Pratt & Whitney developed the JT-33 turbofan engine, known militarily as the TF-33, in the late 1950s. Unlike older, highly inefficient turbojets, these bypass engines were designed to send a portion of the intake air around the engine core, dramatically increasing efficiency, range, and thrust, while simultaneously reducing noise. The military heavily funded the TF-33 to power its massive fleets of Boeing B-52 Stratofortress and KC-135 Stratotankers, as well as the Lockheed C-141 Starlifter. Once this technology was perfected and scaled through lucrative defense contracts, the civilian JT-33 variant revolutionized the commercial sector. It became the definitive power plant for the Boeing 707 and the Douglas DC-8. The Boeing 707, featuring a sleek fuselage and swept wings angled at 35 degrees to reduce drag, became a legendary commercial airliner, dominating transcontinental and international routes for major carriers. Over 1,000 Boeing 707 airframes were delivered, largely utilizing the military-derived Pratt & Whitney turbofans, a technological legacy that allowed the United States to dominate global mass transit, air cargo, and international tourism for the next 60 years. Perhaps the most consequential example of American military procurement reshaping the global economy is the birth of the semiconductor industry. While federal support for computing took many forms, military procurement contracts were the single most influential driver in the rise of the American microchip sector. In the early years of the semiconductor industry, military electronics were heavily isolated from mainstream developments due to unique environmental requirements and strict interoperability specifications. The military viewed technological superiority as an end in itself, a deterrent against Soviet aggression where technical advantages literally separated life from death. Consequently, cost assumed a secondary role. The Department of Defense acted as the crucial first customer for highly experimental technologies. In 1955, William Shockley formed the Shockley Semiconductor Laboratory, recruiting brilliant young scientists to the Santa Clara Valley. Disenchanted with Shockley's authoritarian management style following his 1966 Nobel Prize win, a group of 8 scientists, including Gordon Moore, Robert Noyce, and Eugene Kleiner, later dubbed the Traitorous Eight, defected in 1957 to found Fairchild Semiconductor. Despite the immense challenges of starting a new enterprise, Fairchild secured a vital contract to supply the Air Force with silicon transistors for the supersonic B-70 bomber. The Air Force required transistors capable of withstanding extreme temperatures and delivering fast switching speeds. Because the military was willing to pay premium prices, such as $150 per silicon transistor, roughly 30 times the commercial rate for older germanium transistors, Fairchild was given the capital runway required to survive. The turning point for the global economy occurred in 1958 when Fairchild beat out Texas Instruments to supply transistors for the guidance system of the Air Force's Minuteman intercontinental missile program. The military demanded absolute reliability. A nuclear missile guidance system could not afford a single chip failure. To meet the stringent quality requirements of the Minuteman Reliability Improvement Program, Fairchild was forced to vastly improve and tightly control its nascent manufacturing processes.
The military-enforced discipline yielded massive commercial benefits. The rigorous engineering protocols that Fairchild developed to satisfy the Minuteman program became a major commercial asset. By subsidizing the immense initial costs of miniaturization and reliability testing, the Department of Defense allowed integrated circuit producers to push the frontiers of underlying technology without fear of immediate bankruptcy.
When Fairchild and its subsequent spin-offs entered the civilian consumer markets in the 1960s and 1970s, they leveraged this hard-won manufacturing supremacy to crush international competitors. This military contract directly paved the way for the commercialization of the integrated circuit, the establishment of Silicon Valley, and the entirety of the modern digital paradigm. In the late 20th and early 21st centuries, the Republic of South Korea demonstrated how a highly focused defense industrialization strategy could rapidly elevate a developing, war-torn nation into a global economic powerhouse. Following its liberation from Japan and the subsequent devastation of the Korean War, South Korea was heavily reliant on the United States for the defense of its borders and the supply of its military hardware. However, shifting geopolitical tides in the late 1960s and early 1970s sparked intense security anxieties. The Korean DMZ conflict between 1966 and 1969, coupled with the Nixon Doctrine and the prospect of U.S. troop withdrawals amidst the grinding Vietnam War, terrified the regime of President Park Chung-hee. Recognizing the grim possibility of being abandoned by Western allies while facing a heavily militarized North Korea, Park initiated an aggressive state-mandated policy of Jeju Gukbang, or self-reliant national defense. Because South Korea lacked a foundational heavy industry base, its economy previously reliant on light textiles and agriculture, Park recognized that sovereign military required a complete macroeconomic transformation. Following the Yusin Constitution of 1972, the government launched the Heavy and Chemical Industrialization Plan, HCIP, in 1973. This program was a textbook example of the Mars and Manna concept, where the pursuit of military might, Mars, directly provided the economic sustenance and commercial growth, Manna, that propelled the nation's rapid economic expansion, widely known as the Miracle on the Hangong River. Park's technocrats systematically merged nascent civilian industries with a state-controlled system of indigenous weapons production built entirely from the ground up. The state channeled cheap credit and massive resources into specific strategic sectors over the objections of outside economists: steel, petrochemicals, automobiles, machine tools, shipbuilding, and electronics. Defense industries require a highly synchronized combination of capital investment, industrial infrastructure, and qualified labor. By utilizing the defense mandate to construct these dual-purpose facilities, the HCIP rapidly advanced civilian technology and cultivated a highly skilled labor force. Military technologies were actively diffused into the wider economy through state-mandated spin-off effects, actively supporting the growth of the private sector conglomerates, or chaebols. In just 7 years, 1973 to 1979, this aggressive industrial policy allowed South Korea to leapfrog from an agricultural, aid-dependent state into a highly competitive exporter of heavy machinery and chemicals. The long-term legacy of this independent military modernization is encapsulated by South Korea's current status as the world's 8th largest weapons exporter, fundamentally anchored by advanced platforms like the Chongun-2 surface-to-air missile and the K-9 Thunder self-propelled howitzer. Developed by Hanwha Aerospace utilizing the deep metallurgical and electronic supply chains nurtured over decades of the HCI drive, the K-9 Thunder has emerged as the standard artillery platform for the free world. The platform dominates the global export market, capturing over 60% of international orders, with massive contracts in Poland, Finland, Australia, Norway, Estonia, and Romania. The 155mm caliber system is capable of hitting targets over 40 kilometers away with a rapid fire rate of 3 rounds in 15 seconds, excelling in shoot-and-scoot tactics that ensure survivability. Crucially, South Korea outcompetes traditional Western manufacturers not merely through theoretical engineering perfection, but through a highly pragmatic, Toyota-style approach to defense manufacturing. Because of the massive integrated industrial base established by Park's HCIP, South Korea boasts unparalleled mass production capabilities, robust domestic supply chains, and an intense focus on reliability.
To ensure industrial sovereignty and avoid foreign export restrictions, South Korean firms like STX Engine even developed new domestic engines for the platform. While highly sophisticated European systems like the German PZH-2000 face severe production bottlenecks and immense maintenance costs, South Korea can deliver entire artillery battalions in a matter of months rather than years. The economic and geopolitical impacts of this military-industrial strategy are profound. The K9 export phenomenon has created a lucrative network effect where an expanding user club among NATO and allied nations isolates competitors and drives localized industrial partnerships. For instance, production of the AS9 Huntsman variant in Australia emphasizes local supply chain integration, establishing long-term diplomatic and industrial leverage for Seoul. Likewise, Finland recently signed a €536 million contract for an additional 112 units after operating the system successfully in harsh Arctic weather for 8 years. The Agency for Defense Development at South Korea recently estimated that its 55-year investment of 65 trillion won in defense R&D has yielded an astounding 797 trillion won in combined economic impact. Since its inception, the ADD has developed 303 weapons systems, and its investments generate an average of 6.29 direct and indirect jobs per 1 billion won invested, supporting a massive 380,000 jobs across related industries. South Korea's military necessity has been seamlessly converted into supreme commercial and diplomatic hegemony.
A parallel dynamic of survival-driven innovation defines the economy of the State of Israel. Since its inception, Israel has existed within a highly antagonistic strategic atmosphere, forcing the small nation to maintain a definitive qualitative military edge over its regional neighbors to ensure its sheer survival. Because Israel suffers from severe economic restrictions and limited human resources, it has relied almost entirely on advanced technological dominance. This existential mandate transformed the Israel Defense Forces (IDF) and the National Defense Establishment into the primary engine of the Israeli macroeconomy. When evaluating Israel's status as a global high-tech powerhouse, often affectionately referred to as the startup nation, it is impossible to decouple its commercial economic achievements from its defense-related research and development. During the formative decades of the Israeli technology sector, specifically in the 1980s, the state poured unprecedented resources into military modernization. Defense-related R&D consumed a staggering 3.1% of Israel's GDP, vastly outpacing the 0.84% in the US and 0.58% in Britain, and accounted for 65% of the total national expenditure on R&D. This generated a massive derived demand for highly skilled personnel, engineers, and computer scientists, fundamentally guiding the expansion and curriculum of the nation's higher education institutions. By creating one of the highest concentrations of scientists and engineers in the world, the defense sector directly subsidized the nation's high-tech workforce. Furthermore, as global technology shifted toward information technology and digitalization, Israeli defense contractors heavily utilized outsourcing and dual-use alliances with private civilian firms. The foundational high-tech capabilities built by early government procurement contracts naturally bled into the private sector, allowing Israeli companies to rank among the top global defense corporations while cross-pollinating the civilian market with advanced scientific know-how. The most pronounced example of Israel's military-to-commercial spillover is found in the realm of signals intelligence and cybersecurity, specifically emanating from Unit 8200. Tasked with highly classified cyber warfare and intelligence gathering, Unit 8200 operates as Israel's elite cyber division, frequently compared to the U.S. National Security Agency. As national defense relies increasingly on neutralizing digital threats, the unit requires a constant influx of the country's brightest young minds. However, unlike rigid traditional military organizations, Unit 8200 functions remarkably like a high-tech venture capital incubator. Prime Minister Benjamin Netanyahu noted that because of this specific focus, Israel has become one of the top 5 cyber powers in the world, stating that the tiny nation is punching a bag 200 times above our weight. The organizational culture of Unit 8200 intentionally mirrors the ethos required for successful commercial tech entrepreneurship. Because operational success in cyber warfare requires rapid adaptation, the unit operates with a distinctively flat hierarchy, where function, raw capability, and cognitive traits take precedence over formal military rank.
Young recruits are handed immense life-or-death responsibility at an early age, cultivating extreme resourcefulness, flexible thinking, and a willingness to take calculated risks. Upon completing their mandatory military service, these veterans transition into the civilian sector with unparalleled technical skills, leadership experience, and a highly exclusive professional network forged under extreme operational pressure. The alumni effect of this military unit is profound. Veterans of Unit 8200 have gone on to found over 1,000 technology companies and startups, directly establishing Israel's commercial tech sector. Prominent examples of successful companies founded by alumni include cybersecurity titans like Palo Alto Networks, Checkpoint, and Team 8, as well as mainstream commercial successes like the navigation app Waze. The intense trust established during active duty directly translates into civilian business partnerships, sustained through active alumni associations that facilitate continuous technological innovation. By maintaining close ties between active military reservists and the private sector, knowledge flows horizontally between the IDF and the commercial market. Israel's defense requirements have also catalyzed its dominance in the aerospace sector, particularly in unmanned aerial vehicles, or UAVs. Recognizing the immense risks to manned aircraft from sophisticated anti-aircraft batteries, Israel pioneered the tactical use of drones decades ahead of its peers. During the 1982 Lebanon War, the IDF developed innovative tactics, utilizing early UAVs as decoys to expose enemy radar and anti-aircraft guns, inspiring the United States to take the prospect of military drones much more seriously. This early adoption and relentless battlefield testing provided the Israeli defense industry with an unmatched track record in drone engineering. Consequently, Israel rapidly became one of the absolute leaders in the manufacture, development, and export of UAV technology globally. Military exports serve as a central pillar of the Israeli economy, and the global proliferation of UAVs has provided a highly lucrative growth market. While new competitors like China are emerging to sell to markets closed to Israeli exports, Israel maintains its upper hand through constant innovation and deep integration with European and American defense markets. The foundational engineering, sensor technology, and automated flight algorithms developed for these military UAVs are increasingly converted for civilian and commercial applications, fueling a massive drone tech ecosystem. The immense state investment required to ensure sheer national survival has thereby cascaded directly into commercial robotics, cybersecurity, and civilian technology, fortifying Israel's position as a premier high-tech export economy. The historical record across multiple centuries and diverse geopolitical landscapes indicates a clear causal link between the demands of military procurement and the subsequent economic ascendancy of nations. The state, driven by the uncompromising imperatives of national security, acts as the foundational risk-taker in global economics. By utilizing defense budgets to fund the initial, prohibitively expensive stages of research and development, governments have repeatedly bridged the perilous gap between theoretical science and mass commercial production. The British Empire secured its maritime dominance and ignited the Industrial Revolution because the Royal Navy demanded copper-sheathed hulls, and the Carron Company perfected the casting of the carronade, an effort that directly fueled the refinement of the steam engine and civilian metallurgy. The United States engineered an era of unprecedented global hegemony because the crisis of World War II and the Cold War required strategic bombers, synthetic rubber, and utterly reliable nuclear missile guidance, inadvertently giving birth to the commercial aviation industry and the silicon microprocessor. In the modern era, South Korea leveraged its fear of geopolitical abandonment to build the heavy industry capable of producing the K-9 Thunder, converting national defense into a commercial export juggernaut. Concurrently, Israel's absolute reliance on a qualitative military edge transformed its military intelligence units into the world's most effective high-tech incubator, directly spinning cyber warfare capabilities into civilian tech empire. In each instance, the weapons of war functioned not merely as tools of destruction, but as the raw architecture of the subsequent peacetime economy.